Calculus 3 is composed of vector calculus and multivariable calculus. Traditionally, you should be familiar with a function as having one independent variable and one dependent variable. For example, f of x is a function of x, where the function could be anything like x squared, sine of x, natural log of x, e to the x power, something that's a function of x, and when you go to graph it, it will pass the vertical line test, where it will only have one output. For example, x squared, it will pass the vertical line test because the function will only have one output whenever you put in one input. Other things, such as a circle, fails the vertical line test because it is not a function. For a given input, you do not have one output, you have two outputs. Y squared equals 25 minus x squared is not a function because it fails the vertical line test. It has one input with two outputs. So functions have one input and one output. In calculus 3, vector calculus and multivariable calculus, functions can now be vector valued functions, where you have f of x or f of t, or even r of t is a more common notation. And it will be a vector or a list of components of functions. So you can have a list of functions enclosed by chevrons, such as t, or t squared, or sine of t, or e to the t. And you can have multivariable functions. So instead of f of x, you can have f of x, y, z, t, as many independent variables as you would like. And this would be a scalar function, but you could also have a combination of vector functions of multiple variables. Sine of t, and then you could have x outside of it, plus y squared, minus 3z y t x. Independent variables x, y, z, and t, and the dependent variable you could call something else like w, or in this case it'd be f of x, y, z, t. And in this case, r of t has four separate functions that are four scalar functions. A vector is a fundamental in calculus 3. A vector is similar to a point, but also different. If you were to graph a point on a plane, such as 2, 3, the point describes the location in space from the origin, 0, 0, where 2 indicates positive to the right by 2, and 3 indicates up by 3. At least in Cartesian space, where x, y, and z are orthogonal to each other. The vector 2, 3, similar to this point, is an arrow from the point 0, 0 to the point 2, 3. Vectors always go from one point to another point. This vector is not unique, however. You can have this same vector from point 3, 1 to point 5, 4, and it will still be the vector 2, 3. The vector is defined as the final point minus the initial point, or you could think of tip minus tail. So for this case, final minus initial, and keep it component-wise. So 2 minus 0 is 2, 3 minus 0 is 3. Notice if you switch the order, it is a different vector. If you do 0 minus 2, you get negative 2, and if you do 0 minus 3, you get negative 3. This vector could look similar, as it will be the same line, however the arrow will be in the opposite direction. And you can also notice this is equivalent to distributing a negative 1, or changing the vector to be the opposite direction. In this case, 5 minus 3 is 2, 4 minus 1 is 3. It is the same vector, located at a different origin for it, rather than 0, 0. A unique property of vectors is their length or their magnitude or their norm. I prefer to use the word magnitude as it is universal, but length is the geometric description of the magnitude. Traditionally, the absolute value sign is thought to denote positive values only. However, the absolute value sign means length. For example, on a number line, 5 and -5, the length from 0 to 5 is 5. And the length, if you imagine a vector from 0 to -5, is also 5. Using this definition of magnitude, the magnitude of a vector in 2D space is Pythagorean theorem, where the vector length is the hypotenuse. For the vector 2, 3, the magnitude is the square root of 2 squared plus 3 squared. This is always the case no matter how many dimensions the vector is. For example, vector 2, if it is 2, 3, 6, 4, the magnitude of vector 2 is the square root of 2 squared plus 3 squared plus 6 squared plus 4 squared. Another important fundamental of Calculus 3 is the difference between a scalar and a vector value. A scalar is a single number or a single function, while a vector is a list of scalars. For example, a single scalar function would be this function x squared, while a vector function is a list of these scalar functions t squared, t, sine of t, and e to the t. Some examples of some scalar values or scalar functions are speed, work, power, voltage, temperature, density, or mass. Some examples of some vector values or vector functions are displacement, velocity, acceleration, force, or momentum. For vector functions in 2D space, I recommend thinking back to parametric functions, specifically the unit circle, where x equals r cosine theta, where the radius is 1. So x equals cosine theta. And y equals r sine of theta, where the radius is 1. So y equals sine of theta. The notation for a vector-valued function is always in the order r of t is equal to x of t, comma y of t, comma z of t. For the xy plane, we assume z equals 0. For this example, we can have the vector-valued function r of theta equals x of theta, comma y of theta, comma 0, where x of theta is cosine of theta and y of theta is sine of theta. This vector-valued function represents the unit circle. I prefer to think of the unit circle as a three-dimensional figure. Graphing this out in 3D space reveals a helix where, when looked upon from the xy plane, gives us this circle, and when looked upon from the xz plane, it gives the cosine of theta, and the yz plane gives you sine of theta, where z equals theta, so x equals cosine of z, and y equals sine of z. This combination of three scalar functions gives this vector-valued function that is a helix in 3D space, a circle when viewed from the xy plane, a cosine wave when viewed from the xz plane, and a sine wave when viewed from the yz plane. Scalar functions can be converted into vector-valued functions. However, there is not a unique answer. For example, f of x equals x squared. For functions that are one independent variable and one dependent variable, you can take the independent variable and set it equal to t. And then you can set your function, the y component, if this is on the xy plane, equal to what the function is, substituting t for the independent variable. And the vector-valued function is still in the notation x, y, z, where x of t is equal to t, y of t equals to t squared, and z of t equals to 0, because this is on the xy plane. Notice this is different than the scalar function, and the scalar function gives you every single point all at the same time and does not account for time. Rather, the independent variable in the scalar function is the x position and the dependent is the y position, where in this case, time is the independent variable and the position with two dependent variables is the result of this vector-valued function. A better understanding of how these vector-valued functions work and how they're still vectors is every single time produces a vector rather than a position. For example, what this graph actually looks like, if you were to take it discretely or take selected points, would be a collection from the origin to every given point. If you plug in -1, you'd have -1, comma, +1. If you plug in +1, you'd have +1, +1, +2, +4, and +3, +9. The endpoints of these vectors gives you the shape of the parabola. The reason this solution is not unique is because there can be different time intervals that represent the same exact position. For example, I can replace every one of these t's with t minus 3, and I will still have the same exact function with different time intervals representing the same position. For this function, the time 0 represents the vector with magnitude 0 that is at the origin, while for this function, the time 0 represents the vector -3, +9, 0. And the vector at the origin for this function will be at time 3. A challenging example that demonstrates how the vector-valued function is not unique is a representation of the top half of a circle with the yz plane. The scalar function for this could be represented z equals the positive square root of, and we'll say that is radius 5, 25 minus y squared. We can represent the independent variable as time, the dependent variable as the function of time, and since this is planar, x of t is going to be the one that equals 0 for the yz plane. Keep the corresponding order x, y, z. To specifically represent this top half of the circle, we need to bound the time. Another representation of the top half of the circle could be similar to that parametric form that I just talked about earlier, where x equals r cosine theta, where in this case the radius is 5. But in this case, it is y equals 5 cosine of t, because the horizontal left and right variable is y, not x. The z of t, similar to what we thought was the y of t in the xy plane example, is going to be r sine of t, where the radius is 5. And then again, we're in the yz plane where x is 0. Keep your vector function in the form x, y, z. We need to bound our time to be the top half of this circle. To find these time bounds, you plug in one of the bounds and see if you get the position that you want. So I plug in 0 for all the t's, and I should get the position where the x is 0, the y is 5, and the z is 0. So I get 0, cosine of 0 is 1, multiplied by 5 is 5, and then sine of 0 is 0. So 0, 5, 0. And that is the position here at time 0. And at time pi, I get the position here. And notice that there is direction along this path. As time increases, it travels counterclockwise. For this function, as time increases, it travels clockwise. A third representation of this top half of the circle would be swapping the cosine and the sine. Since both are oscillating functions, they can be interchangeable as long as the time bounds correspond with the top half of the circle. Think of this as rotating the circle 90 degrees, as sine and cosine's difference is just 90 degrees. So the time bound would need to be shifted by 90 degrees, or pi over 2 radians. You just need to make sure your position matches. Notice these are 3 different vector functions that represent the exact same top half of this circle. A vector function is not a unique representation of this path. However, there is infinitely many ways to represent this path traveled with different time intervals. There are 3 common vectors or standard vectors in Calculus 3. These vectors have all of their magnitude in one orthogonal axis, the vector 1, 0, 0 has all of its magnitude in the x-axis direction, the vector 0, 1, 0 has all of the magnitude in the y-axis direction, and the vector 0, 0, 1 has all of the magnitude in the z-axis direction. Because these vectors are length 1, they are known as unit vectors, and are named I, j, and k, corresponding with x, y, and z. These vectors are also known as I hat, j hat, and k hat, where the hat implies unit vector. If you ever see a hat over a vector, it implies it is vector of length or magnitude 1. Another representation of a vector-valued function is using the I, j, k format, where any coefficients to the vectors I, j, and k are scalar values to distribute to each of the components of the vectors I, j, and k. For example, this vector r of t can be written in ijk format, distributing the scalar to each of the components of the vectors and then summing the vectors with vector operations component-wise will result in the original vector we started with. When adding vectors in vector operations, you add component-wise. 0 plus 0, 5 sine t plus 0, and 0 plus 5 cosine t. You could think of the I, j, and k as the place values between the commas. Remember to have plus signs though. So earlier I had mentioned that a vector has both magnitude and direction. However, sometimes we can use a vector to represent only the direction by dividing out the magnitude. For example, if you're given the vector 3, 3, when you graph it out, it has both direction and length. If you divide this vector by its magnitude, it only represents the direction with length 1. This is a familiar case with a 45, 45, 90 triangle. The magnitude of vector v1 is equal to the square root of 3 squared plus 3 squared, which in this case is 3 square roots of 2. Therefore, if we only wanted to represent the direction without the magnitude, the vector v1 as a unit vector, or v1 hat, because the hat implies unit vector, would be equal to each of the components divided by the magnitude. So in this case, it would be 3 divided by 3 square root 2, comma, 3 divided by 3 square root 2. Notice the 3's cancel and you're left with 1 divided by the square root of 2 for each of the components, or square root of 2 divided by 2 if you rationalize it. You can then check that this unit vector is length 1 by using the Pythagorean theorem. You should be familiar with this specific combination from the unit circle at 45 degrees, and the unit circle is radius or hypotenuse of 1. Therefore, if you wanted to represent the direction only of vector v1, you can use the unit vector that only gives the direction without the magnitude. This is useful as you can now distribute any scalar or magnitude value to this unit vector to give it the same direction as v1. Thank you for watching. Let me know if you have any questions.